This is the video version of the talk for STOC 2023 paper, Resolving Matrix Bansal Conjecture up to Poly-logarithmic rank. My name is Haotian. I'm a postdoc at Microsoft Research Redmond, and this is joint work with Nikhil Bansal from the University of Michigan and Raghu Meka from UCLA. Okay, so let's start with the classical discrepancy problem. In this problem, we are given a universe of n elements and subsets S1 to Sn. So here, I'm assuming that the number of subsets is equal to the number of elements in the universe, which turns out to be the most interesting case. Our goal is to color the elements red or blue so that each set in the set system is as balanced as possible. More formally, for a coloring, let's think of the red elements as -1 and the blue elements as +1s. Then the discrepancy is defined as you take the maximum over all the sets Sj in the set system. For each Sj, you look at the sum of the color of elements that lie in Sj. This is the imbalance of the set Sj, and you take the maximum over all Sj. This is the worst imbalance of any set in the set system. And this is exactly what discrepancy is trying to capture. And of course, our goal is to find a coloring X to minimize the discrepancy of the coloring. Okay. So it turns out there's a different view of the same problem. It's a vector balancing view. And for this, you look at the incidence matrix A of the set system. This is a 0-1 matrix whose rows correspond to sets and columns corresponding to elements. Now, for a set for row Sj and a column, which is an element I, the entry Aj, this is equal to 1 if the element I lies in Sj and 0 otherwise. Okay, so now if you denote the column vectors of this matrix as A1 to An, then for any coloring X, which is a ±1 vector, I claim that the sum of Xi for I in Sj is exactly the same as the sum of Xi times the jth coordinate of each column vector Aij. Why? Because Aij is 1 if I lies in Sj and 0 otherwise. So the sum on the right-hand side only picks up those terms, I, that lies in Sj. So that's exactly the left-hand side. So now if you take the maximum over all the set Sj, we reach the discrepancy which we defined on the first slide. This is exactly the L infinity norm of the sum of Xiai. Okay, so now you can view this question as you're given these column vectors A1 to An, and you want to find a ±1 assigning of these vectors to minimize the L infinity of the sign sum. Okay, so it turns out there's nothing special about the matrices coming from being an incidence matrix. For the same set of techniques would work for any matrix whose entries are between -1 and 1. Okay, so if you're given such a general matrix and you denote the column vectors as A1 to An, then we reach the following more general vector balancing question. So you're given these vectors A1 to An, each has L infinity norm at most 1. Our goal is to find a ±1 signs to minimize the L infinity norm of the sign sum. Okay. So this more generally, discrepancies study how to divide a group of objects into two similar groups. In the previous example, it's dividing vectors. And this is related to many other areas studied as early as the 1930s. It's related to computational geometry, complexity, sampling, and many other areas. These are two very nice standard textbooks on this topic. So now I want to talk about one of the most foundational results in discrepancy by Spencer. So let's recall our problem. We are given these vectors A1 to An, each has L infinity norm at most 1. Our goal is to find ±1 signs to minimize the L infinity norm of the sign sum. So the most natural strategy when you first encounter such a problem is to pick the signs uniformly random. And if you do that, the discrepancy is typically on the order of square root of n log n. I will use this notation throughout to mean that the left-hand side is at most a constant times the right-hand side. Okay, so why is that? So if you denote the discrepancy of row J, this is the absolute value of sum of Xi times the jth coordinate of Ai. We call this discrepancy of J. Then, because we pick xi to be random plus minus ones, and aij is most one, the absolute value. So discrepancy j has the most square root of n standard deviation. It also has a Gaussian tail by Chernoff method, so the probability that discrepancy j exceeding t times root n, this is at the most e to the negative t squared. So if you pick t to be a constant times root log n, then the probability here will be at most 1 over poly n. So you can do union bound. This shows the discrepancy is typically on the order of square root of n log n. Turns out this analysis is tied up to a constant factor. And in a very surprising result, Spencer showed that you can actually find one color which for which the discrepancy is at most a constant times root n. So the extra square root of log n should not be there. And Spencer's result is also tied up to a constant. So this result is foundational to discrepancy theory because it shows the crucial difference between the typical and extremal behavior of a discrepancy of a random coloring. But its original proof is non-algorithmic. However, following a breakthrough by Bansal in 2010, who gave the first constructive version of Spencer's result, there has been a burst of progress on designing efficient algorithms for discrepancy problems. And because the rounding error is closely related to discrepancy, this is first shown by Lovat, Spencer, and Vestergabi, there has been a growing list of algorithmic applications of discrepancy theory to approximation algorithms, graph sparsification, differential privacy, randomized controlled trials, and many others. So I'm not going to dive into these applications. What I want to do now is to discuss a matrix analog of Spencer's setting. So instead of giving vectors, we're now given n by n matrices A1 to AN. Instead of having our infinity norm, we assume that each matrix AI has operator norm at most 1, and discrepancy is also measured in terms of the operator norm. So what is the operator norm of the matrix? Well, it's the maximum singular value of the matrix. In the matrix symmetric, this is just the maximum absolute value of all its eigenvalues. For example, if a matrix A is diagonal, then the operator norm of A is just the infinity norm of its diagonal entries. And this shows that the problem I defined here, for this problem, more general problem, the diagonal case is actually Spencer's setting. Why? Because if each matrix AI is diagonal, then you can define a vector corresponding to its diagonal entries, and the L operator norm of the matrices will be equivalent to the L infinity norm of those diagonal entries. So this shows that this matrix analog of Spencer is really a generalization of Spencer's setting. And similar to the case of Spencer, if you pick the signs xi uniformly at random, then the operator norm is typically on the order of square root of n log n. Okay. But unlike the diagonal case, even this result is much trickier to prove. And the main reason is because once you have matrices that are not diagonal, then AIAJ is no longer equal to AJAI. And this causes a lot of problems for generalizing the proof that I showed you in the first few slides for the diagonal case. It actually took people quite a long time to realize the correct set of tools to prove this result, and these are called matrix concentration inequalities that I will discuss later. And so similar to the case to Spencer's setting, it was conjectured independently by Zosius in 2012 and Meka in 2014 that this extra square root of log n can be removed. So it is conjectured that there should exist a coloring. So the discrepancy is on the order of square root of n. Okay. So why should we be interested in this matrix generalization of Spencer's result? So I will discuss two main motivations. The first motivation is what is called a quantum random access code, studied widely in TCS, quantum physics, etc. Since the seminal work by Ambani, Nayak, Tashma, and Vazirani in 2002. Okay. So the setting is the following. So we have Alice and Bob, and Alice holds a string of plus minus ones. And now she wants to send a quantum message rho to Bob. And upon receiving the message rho, an adversary comes and say, hey, Bob, guess me, what is xi? And Bob wants to guess xi correctly with as high probability as possible. So there are two extremes of this problem. Alice could have sent the entire message x to Bob, which is n bits of classical communication, and Bob could guess every bit correctly with probability. And of course, Alice could have sent no message at all, and Bob could not do better than a random guess. So quantum random access codes study this fundamental trade-off between the success probability and the amount of communication in terms of qubits, the trade-off between these two quantities. And it turns out this problem is closely connected to the matrix-Spencer conjecture. This was observed in a prior work by Hopkins, Raghu, and Shetty. The idea is that if you have matrices A1 to AN, that has large discrepancy. This means for any signs xi, the sum of xi ai has large operator norm. So it has a large eigenvector v. Then you look at v transpose the sign sum times v. You can rewrite this as the sum of xi times v transpose ai v. Okay? And this should be large for any coloring xi. Okay, for any coloring xi, there exists such a v so that the sum of xi times v transpose aiv is large. This basically says v transpose aiv is correlated, has a non-trivial correlation with xi. So Alice could have just sent the quantum state v transpose to Bob, and Bob could guess xi correct with non-trivial probability. So a second motivation is this area called matrix concentration inequalities, where a typical question that's studied is what is the typical value of the operator norm of sum of xi ai for random plus minus one xi's or standard Gaussian xi's. So this question has a lot of extensive applications to many different areas, but it is not fully understood for general matrices AI. And it turns out that resolving the conjecture might give new insight into this space of questions as well. Okay, so what do we know about the matrix-Spencer conjecture? Well, there are several special cases where the conjecture has been proved. The first special case is the block diagonal case. This is a generalization of Spencer's classical setting of diagonal matrices to block diagonal matrices. This was first shown by Levy, Ramdas, and Rothfuss in 2017, and generalized by Dadouche, myself, and Race in 2022. Okay. But this direction is going to be very orthogonal to what I'm going to talk about. A more relevant case is the low rank case. And it was proved by Hopkins, Raghu, and Shetty last year that the conjecture is true under the actual assumption that the rank of each matrix AI is at most root n. But before discussing this result, why is the low rank case even interesting? This is a valid concern because for the Spencer setting or the diagonal case, if the matrix is rank R, that means the diagonal entries are sparse. But Banashek, over 20 years ago, already showed that if you have R-sparse diagonal matrices, then the discrepancy is at most square root of R log n. Okay? So imagine taking R to be root n, then Banashek's result already gives roughly n to the 1/4 discrepancy for rank R matrices, for rank R diagonal matrices. Okay? So this is much smaller than what the conjecture asserts. However, for the full general matrix-Spencer question, in Dadouche, myself, and Race proved that even if you assume the matrices are all rank 1, that there's already a lower bound of root n. So this shows that the full problem is very different from the diagonal case, and the low rank case for the full problem is already very interesting. Okay, so our main result of this work is that if the matrices AI all have operator norm at most 1, and additionally the rank of each matrix AI is at most n over log n cubed, so this is nearly full rank matrices, then the discrepancy is at most the constant times root n. So this improves the work by HRS from rank root n to almost full rank matrices and resolves the conjecture up to polylogarithmic rank. So, right? And it turns out that these signs X i's can be found efficiently using standard techniques from algorithm discrepancy, but I'm not going to go into that. Okay? And because by this connection to quantum random access codes observed by HRS, this gives a nearly optimal lower bound for quantum random access codes in the corresponding region. Okay, so now I want to discuss a few key techniques behind the proof of this theorem. So the first tool that we use is the partial coloring method. And this is a key tool in discrepancy theory invented around the 80s and refined by Spencer in 1985 to prove his fundamental result. Okay, so what is a partial coloring? A partial coloring is a plus, minus, 1, and 0 vector with at least a linear number of coordinates being plus, minus, 1. So this is a relaxation notion of a coloring where you allow some coordinates to stay at 0. Okay, but at least a linear fraction, a constant fraction of the coordinates must reach plus, minus, 1. And turns out, so the point of a partial coloring is that if you can find a partial coloring with discrepancy root n for the setting that we considered, then you can get a full color with discrepancy at most a constant times root n. So why is this? Okay, so if you look at, here's a animation, and we're counting the discrepancy of each phase. In the first phase, I'm going to use the partial coloring method to find a partial coloring with discrepancy root n, okay, and a current discrepancy root n. And in the second phase, I'm going to apply the same partial coloring result on the remaining set of elements which are not yet fully colored. And I get discrepancy root of n over 2 because they're only, I assume that I color half of the elements and there are only n over 2 remaining. So I'm going to do this on the remaining set of uncolored elements until everyone gets colored. Okay? And I incurred a discrepancy, which is a geometrically decreasing sequence, which sums up to a constant times root n. Okay, so this basically says that finding partial coloring suffices to prove Spencer's fundamental result and suffices for the matrix Spencer conjecture as well. So how do we find a good partial coloring? Okay, now I'm going to, okay, so let's look at this geometric view of partial coloring. Let's define the discrepancy body K as the set of all fractional vectors X for which the operating norm of sum of xi ai is the most constant times root n. This is constant, the constant you can pick as large as you like. So this is the set of all fractional colorings with discrepancy at most a constant times root n. And this is in general, this body can look very, very complicated, but it's a symmetric convex set. Okay. And our goal is just to find a partial coloring inside K. Okay, because if we find a partial coloring point inside K, then by definition, this partial coloring would have a discrepancy at most a constant times root n. And it turns out there's a standard method based on convex geometry for finding a partial coloring inside a convex set. And this is by looking at the Gaussian measure of K. So what is the Gaussian measure? This is where you pick a standard Gaussian vector G, and you look at what is the probability that this Gaussian vector G lies inside K. Okay? The Gaussian measure is basically sort of the Gaussian mass inside the mass of a standard Gaussian vector, a Gaussian distribution inside K. Okay? And in the sample result, Gluskin in 1989 and Giannopoulos in 1997 proved that as long as the Gaussian measure of K is at least e to the negative constant times n for some small enough constant, then you can find then there exists a partial coloring inside K. Okay? And this can be made constructive. You can algorithmically find this partial coloring in K due to a work by Rothfuss. Okay? So the main question now reduces to how do we actually prove that the Gaussian measure of K is at least e to the negative constant times n. So for Spencer's setting, or the diagonal case, this discrepancy body K becomes the L infinity norm of the sum of xi ai being at most a constant times root n. And this is a polytope with at most 2n constraints. Okay? So K is the sort of if you look at every coordinate of this L infinity constraint, then K is the intersection of all these different slabs. Okay? And by Sidak's lemma, the Gaussian measure of K would be at least the product of the Gaussian measure of each one of these slabs. And if you pick the constant on the right-hand side to be large enough, then each one of these slabs would have as big a constant of Gaussian measure as you want. So this will give you the sufficient Gaussian measure lower bound. But does this same strategy work for matrix expansor? So for matrices, the discrepancy body K has this operator norm constraint. And this means U transpose the sign sum times U is at most a constant times root n for all unit vectors U. And if you discretize, this is still an exponential number of constraints. So you cannot use the same technique for as in the diagonal case to prove the Gaussian measure lower bound for K. Okay, so what are we going to do now? So let's go back to the definition of the Gaussian measure of the discrepancy body K. This is the probability that a standard Gaussian vector G lies inside K. Okay. So if you write this out, this is the probability that the sum of GIAI has operator norm at most a constant times root n for IID Gaussians GI. So to understand this, we need to understand the behavior of the operator norm of sum of GIAI, and this has been extensively studied in random matrix theory. So in general, for a random matrix of the form sum of GIAI, where GI are IID standard Gaussians and AI are deterministic symmetric matrices, then X has Gaussian entries. Okay, but these Gaussian entries could have arbitrary correlations. But it turns out that you can still say something about the typical value of the operator norm of X in terms of the components matrices AI. For example, the non-commutative Kinch inequality by Las-Pickard and Pizier asserts that the typical expectation of the operator norm of X, this is up to a root log n factor, this standard deviation parameter sigma of X. Okay, so what is sigma of X? Sigma X squared is defined as the operator norm of expected X squared. And if you expand this out using GI being IID standard Gaussians, this is just the operator norm of the sum of AI squared. Okay, so this is a actually very amazing inequality because just using second order information, you can already pin down the typical value of the operator norm of X up to a root log n factor. However, for matrix expansor, sigma X is square root of n because each AI has the operator norm of 1. So this gives the random coloring bound of root n log n, as we claimed earlier, which is not sufficient for proving matrix expansor conjecture. Okay, but luckily, recently there has been this breakthrough by Bandera, Haotian, and Bansal, who proved a more refined version of the non-commutative inequality. They proved that the expected operator norm of X is the most sigma X plus a different parameter V of X times poly-logarithmic factor. Okay, so what is V of X? This is the operator norm of this matrix, of this covariance matrix of X. So this covariance matrix of X is where you view the random matrix as a n squared dimensional random vector and look at the covariance matrix of that random vector. Okay, so roughly this captures more refined structures of AI, which I'm not going to dive into in this talk. Okay, but the point here is that now the poly-logarithmic factor moves from the sigma of X, which is root n for matrix expansor, to this additional parameter V of X. And here's how we can use this result for matrix expansor. So all we need is that this additional parameter V of X is the most sigma of X over a poly-logarithmic factor. Okay? Then this result by Bandera, Haotian, and Bansal directly implies the random coloring would have discrepancy root n. Okay? However, this is of course not true in general because we know random coloring has big discrepancy. But for low rank matrices AI, if here low rank means the rank of AI is n over polylog, then you can actually prove that this, here's the typo, there's the covariance of X, this matrix covariance of X has only sparse large directions. So we can afford to condition on those directions being small and prove that the probability that the operator norm of sum of GIAI being at most root n is at least an exponential factor. So you pay an exponential factor for controlling all these large directions of the covariance matrix. Okay? But that's sufficient for us because this already implies a partial coloring for matrix Spencer. Okay, so just to so these are the main ideas for proving the main result. And just to summarize, we show that the matrix Spencer conjecture is true, assuming the rank of the matrices is most n over polylog. And the main ideas is that to use this sharp matrix concentration inequalities together with controlling large directions. And this will imply a e to the negative some small constant times n Gaussian measure lower bound for the discrepancy body. And then this implies partial coloring by standard tools. Okay, so the open problem on post here is, can we fully resolve the matrix Spencer conjecture? And it turns out the full rank case seems to be quite different from the nearly full rank case, and our proof does not quite generalize that case so far. Okay, and that's everything. Thank you everyone for listening.